Recording. All right, welcome
Okay.
to the September meeting on the Stockton Astronomical Society. Our fearless leader, Tim, is on a hike.
Mm.
Doing the Tahoe Rim Trail. He sent me a picture this morning. And
Oh.
maybe Eric can toss that up on the screen. He had it. But he's about halfway through. That was what I got dinged this morning at about 6 a.m.
Let me share it with Zoom land here.
Yeah, that would be great.
Yeah.
I'm like, wait, what picture?
Mm.
You guys got it?
Oh, cool.
So anyway,
That's a nice picture of Tahoe.
Yep. So like I said, Tim's out there, so that means you guys get B team as in me for running the meeting. So I'm going to introduce our speaker, who actually really doesn't need any introduction since she's one of us and has been one of us for over 10 years now. Our newsletter editor, are working on her PhD, now has her master's at UCLA. Okay, and she's going to be talking about our galactic center. So we're going to go from the suburbs where we are, and we're going to head to the big city around the big black hole, and she's going to talk about that. So,
Okay.
without further ado, Rebecca, the floor is yours.
Ooh, I thought there were usually
slot.
I thought there were usually announcements beforehand, but I can take it away. Can I share my screen? I think someone else has to stop sharing.
Go ahead and
Okay.
try to start anyways, because I'm having trouble finding it now.
Uh-oh.
It says you cannot start screen share while the other one is doing it.
There we go.
Okay,
Okay.
cool. Okay, I'm going to open slideshow so that it's big. Let's see what
Mm.
Okay, let's hope this works fine. Okay, wait, I'm just going to check to make sure that it flips between slides correctly. Okay, is the screen changing?
Yes.
Okay, cool.
Got it.
All right. Hello, everyone. Thank you so much for that and for the introduction. As was just said, I'm Rebecca Lewis-Merrill. So I'm currently in my third year of my PhD program in astrophysics at UCLA. I study the Galactic Center. In January, I gave a talk on Titan, which was undergrad research that I had done. However, the Galactic Center is where I have been sequestered for the past 4 years, actually, because I started doing research there in undergrad and then did some during my gap year between undergrad and grad school, and I'm still here. I work with Dr. Tuan Do and Dr. Matthew Hosek. They're both wonderful people. And I assure you both that I am in very good mentorship hands. Y'all got me off to a great start and told me essentially showed me what I should look for in mentors, and I found some here. So, so tonight we're going to be talking about star formation in the Galactic Center, and I'm going to be giving y'all a tour of the mysteries therein. This talk is going to be to a general level, and I'm going to explain any particulars that need to be understood in order to get anything that's slightly deeper than just general sky knowledge. Okay, so first of all, well, I was going to ask for a show of hands, but I can't see the entire room. Who knows where the Galactic Center is on the sky?
I think most of us do.
Okay. Okay, we got a couple hands. Okay, so this is review. Okay, so the image that you currently see on the screen here was taken on top of Mauna Kea at the Keck telescopes. The two beams of light that you see emitting from them are lasers that create artificial stars in the sky that we use to correct for atmospheric turbulence. So rather than having to rather than just having to deal with all of the atmospheric turbulence in our images, we can correct for it. This is continually, I would like to say, a pain in the butt a bit, because we have to shut them off intermittently because of satellites going by, and that's regulated by US Space Force, actually. So the Starlink satellites are particularly annoying for this. But so both of these lasers at the time are pointed at the Galactic Center because the lab group had time on both the Keck 1 and Keck 2 telescopes at the time. Each telescope has different instruments on it, which is why we were interested in having time on each of them. So during this night, we were taking both images using one instrument and one telescope, and spectroscopy using the other telescope on a different instrument. So pointed toward the constellation Sagittarius on the sky, if we go in closer, this image is, darn it, I forget the exact field of view of this. But at this point, you can start seeing some of so this feature here are how we usually locate where we are in an image when I'm just looking at a random snapshot of data from the Galactic Center. But Sagittarius A star is the black hole plus accretion disk at the heart of our galaxy. So when I say black hole plus accretion disk, so around the black hole, as matter falls toward the black hole, it forms into a disk similar to it falls into a disk, and as it rubs against each other, it loses friction and starts to essentially swirl into the black hole. So you can think of this matter as draining into the black hole. However, in this disk, because all the material is rubbing against each other, it's heating up. And this comes out as infrared light. So this accretion disk glows in multiple wavelengths. So we can actually see the black hole, in the sense of we can see its location due to the light emitted from its accretion disk. So whenever I say like the brightness of Sagittarius A star, when I say Sagittarius A star, I mean the black hole plus this light emitting component. Any questions on that before I continue?
Yeah, so what kind of wavelengths are you guys looking at approximately?
So the wavelengths, so the wavelengths that the Galactic Center group tends to use, are infrared wavelengths, and the one we use the most is K band, which is 1.27 microns.
Okay.
However, Sagittarius A star is also very bright in radio. So radio is often used to sort of track the location of Sagittarius A star. It's a separate conversation, but in order to really figure out where to build like a steady reference frame to measure the velocity, you actually need to use both radio and infrared observations. Any other questions? Not, I shall continue on. Okay, so I will continue to zoom in. So this is the general environment that I tend to work in the Galactic Center, and where we'll be talking about star formation. So this area is about the inner 30 light years to Sagittarius A star. That ends up being a sphere with a diameter of about 10 parsecs, which is about 30 light years. So we're starting out at this red bit of the cartoon is the nuclear star cluster. So nuclear star clusters actually form at the centers of most spiral galaxies. So at the centers of spiral galaxies, that is the area where matter tends to congregate. And so you end up having a very deep gravitational well at the center of the galaxy. So you can think of the gravitational well sort of sloping down a lot toward the center of a spiral galaxy. So stuff will sort of fall into that well, leading to nuclear star clusters that are incredibly dense. They tend to be old stars as well, which are low mass. So they end up being very red and high density areas. And when I say high density, what I mean is, so if you imagine the 4 light years between us and Alpha Centauri, Alpha Centauri is our closest star, about our closest star, and that's about 4 light years away, if I recall correctly. At the galactic center, in the area I'm talking about, you would have 100 stars between us and Alpha Centauri. So the average distance between stars goes up by a factor of 100. And this leads to stars interacting with each other on a very regular basis. So if you're doing any calculations on where's that star going to be next year, you have to take into consideration the other stars around it. And in the next panel, can you see my cursor?
Yeah.
Yes, we can.
Okay. So if we go in further, this blue circle here, this is the, I went too far. This is the young stellar cluster. So the young stellar cluster is about the inner parsec, so that would be about the inner 3 light years. So we've gone in by about a factor of 10. So in about the inner 3 light years, we actually have essentially a ball of young stars around the black hole. And these are very high mass stars, generally O and B type stars. Does anyone not know why a high mass star must be young?
Burns fast.
No? What?
Burns fast, dies quick. Yep.
Yeah. So by this point in the history of the galaxy, if these stars were any older than a few million years, we wouldn't see them because they'd be dead already. So, and then when we go into the inner about 0.01 parsecs, which is about, we'll say about the inner 10th of a light year, I think we're getting to, is the S star cluster. The S star cluster is so named, I believe, after Sagittarius. But these are stars that have orbits around the central black hole. So generally all of the stars out through the nuclear star cluster feel the gravitational pull of the black hole in some fashion. However, the S stars are ones that very distinctively have accelerations in their motion, so they curve as they move across the sky. So you can tell, so after a period of say 20 years, which is what we do have data for, you can mark out the orbit of the star. And then at the center you have the black hole. So beyond being able to see the black hole in infrared due to its accretion disk, the Sagittarius A star was identified as a black hole due to the compact mass determined to be there by the orbits of these stars over time. So while this is all well and good, we wouldn't actually expect there to be stars around a supermassive black hole. Here's where we start getting into problems. Okay, so quick overview. Formation of a star comes from collapse of a gas cloud. So in a giant cloud of gas and dust, mostly gas, you have turbulent motion inside due to exterior forces acting on the cloud, usually shock waves from other objects moving by, or some star decides to explode, etc. So you end up with higher density clumps inside of the cloud. And that's what we're looking at here. So this is a clump inside of a molecular cloud. So this clump has hydrogen particles inside that have temperature and so have thermal energy and are whizzing around. So this whizzing around means that they have an outward pressure that's being applied, such as if you were blowing up a balloon. When you blow up the balloon, there's pressure added to the walls of the balloon by the air you put inside, so it's supported. However, at the same time, this clump has a substantial amount of mass and so has gravity trying to pull it all back together. So as long as the internal pressure can support it against gravity, it doesn't collapse. However, if the gas cloud accumulates enough mass with the gravitational pressure, but we don't increase in temperature, so we don't have an increase in outward pressure, then gravity wins and it collapses. And this collapse continues until as it collapses, it starts heating up, and then eventually you get a protostar that forms. Now, black holes are really good at stretching out gas. And this is a problem because when you stretch out a bunch of gas, then you decrease the density of it. So you don't get large enough clumps. So around a black hole, you would expect any cloud of gas to be too disturbed, too blocked out to actually form a star anywhere near it. So these plots here are, explaining these plots, the color here is a density measure. So darker red means higher density. So we start out with a little clump of gas that moves in toward a black hole that's around here. And as it approaches, it gets pulled out because the force closer to the side closer to the black hole is experiencing more gravity than the side that's further away, so it gets stretched out, and then it's still trying to continue along its path, and it ends up as this elongated sort of gas streamer. And you can't make a star from that. However, we see stars. We see a lot of stars. We see a lot of stars that are young. But we don't see any molecular clouds really near Sagittarius A star either. So this conundrum is often called the paradox of youth. I have no idea who coined it, but everyone I ask about it kind of sardonically says, yeah, paradox. But at the same time, I kind of think it fits, because no one has a good explanation for me of why everyone agrees, yeah, we wouldn't expect stars there, but yes, we see stars there. And I haven't found any good papers that explain how they should have formed. So it's up for debate on how do we have the young stellar cluster at all. So this plot is just some orbits of young stars around Sagittarius A star. And this is actually an animation of S stars or young stars that we have observed near Sagittarius A star since 1995, actually. This data set is older than I am. Actually, the last grad student in the group that was older than the data set just defended her thesis and moved on to a faculty position. So all of Andrea Gez's newer grad students are all younger than the data set. Yeah, so that's our first mystery, the paradox of youth in the galactic center. Any questions on that before I continue?
I have a question. This is Eric.
Okay.
Could the young stars have developed further away from the black hole, and then either the black hole, I guess, it had moved in toward the black hole at a later time?
Yeah, so there have been simulations done of how long would it take stars to migrate into where they are at the galactic center, and the stars would have died before they got there. So they had to have formed, as far as we can tell, they had to have formed in situ, which means where they are.
Okay.
So we know that black holes are messy eaters, so we're assuming that the gas is from the shredded stars that, I mean, it has taken in before we were able to look at it. I mean, before we started looking at it, when there was possibly more, when it was actually eating. So there'd be
Either that or mass that has just sort of fallen in. Let me go back to an earlier slide. Here. So these sort of tendril-like things looking here, it's called the mini spiral because of how it looks, but these are actually streamers of gas that are actually infalling towards Sagittarius A star.
Right.
So we do have infalling gas, but nothing really to the scale of a molecular cloud, like with the right density.
Right.
It's all very hot gas that, because it's so hot, it's very low density because it doesn't like to come together because it's hot. It's hot, and so the gas is, for lack of a better word, fluffy.
Right.
So yeah, so it's all low density, very hot gas. But there is gas, lots of gas in the galactic center.
Right, but you've got so many stars flipping around that black hole that the gravity waves around that thing's got to be so choppy that you're gonna have low density areas gravitational wise and real high density things crashing into each other constantly, wouldn't you?
Yeah. In addition, because these are all O and B type stars, any of them could go supernova at any given point.
Right. So like you said, you just have it'd be a cacophony of gravitational waves in that area, which could bring material together, slamming the material together that wouldn't normally come together gravitationally in a calm area, is what I'm
Yeah.
questioning.
So I would, so, and we come back to the heating issue. So with all that turbulence, you have gas that is hot, and hot gas doesn't like to form stars.
No, but if you've got
Yeah.
gravitational forces forcing it this way, you know, from two different directions coming at it, it would overpower any molecular movement in that cloud. What I'm saying is that normally stars form in a very quiet area, so your
Yeah.
gravity is pretty much stable. But around that
Mhm.
black hole, you've got to have gravity waves that are just huge, much
Yeah.
denser things crashing together constantly. And so that's why
Yeah.
if that's where you guys are looking at why it's able to overcome the hot gas, the molecular movement of the hot gas, is because the gravity is so much different in that area.
Yeah. And the wonkiness of the gravity well in this area has given many theoretical astrophysicists I know a headache. Madar Niles has an entire lab group dedicated to this kind of thing. But on whether or not that would be enough to form stars, I don't know. Unfortunately.
You probably don't know enough about the gravity waves in that area.
Yeah, because as turbulent as it might be, they're still very small compared to what we can detect at this point. Once LISA, the gravitational wave observatory in space, goes up, we might be able to detect them. But currently, the seismic floor, which is just the rumbling of the earth being like the floor of, we can't detect anything longer than that. Yeah, so even if it might be choppy, we don't know the characteristics of the gravitational waves in the galactic center yet, as far as I know. I'm sure there's simulations, but I haven't read those papers yet.
Probably the realm of this modelers using supercomputers at this point instead of what you can actually measure.
Yeah, I'm much more an observationalist.
So, okay, that was the end of my query.
Thank you. Well, thank you for the thank you for the query, not the
Moving right along.
what?
Moving right along.
Moving right along. Okay. Next thing. Not only do we have weirdly young stars at the galactic center, we also have just weird objects in general. Okay, let me introduce you to what are currently called the G objects. Okay, so the G objects are okay, so this is a picture of essentially visualized gas and dust in the galactic center. And the G6, G3, G4, G5 are pointed to the G objects in particular. So the G objects themselves appear in our infrared data as very dim, gaseous, blob-looking things. But they're pretty compact. And they go on orbits. So they don't. So the big weird thing about them is that their spectrums just look like heated gas, but they act like stars. So they are compact things that look like they're low density. so, so these are some modeled orbits of the G objects. And this is actually an image I showed earlier, but this was originally a model of if the object G2 was an ionized gas cloud, because G2 was going very close to the black hole in the last 5 years. And so people were thinking that, oh, it's going to go close to Sagittarius A star, it's going to drop matter on the black hole, and we're going to see a flare of activity. But G2, so this is what we thought was going to happen. And then this is what actually happened. So we see G2 plotting. So this is another image of G2 in a different format. So we have G2 plotting along, and 2012 comes, and then it's about to go into its periapse, but then it just shows up again, and it just keeps going along. So we expected it to become this giant streamer thing, but it stayed compact. But it is, to all appearances, a gas cloud. So there are multiple theories on what the G objects are. These range from intermediate mass black holes that have attracted dust and gas around them to make them look like they have a dusty shroud. They might be protostars that still have a lot of gas and dust around them after their formation. The leading theory is actually that they're the result of binary stars that have essentially inspiraled to each other because their orbits were disturbed by the black hole, which would lead to a bunch of gas and dust, but also a stellar core that would be able to keep that gas and dust around it. However, we can't really see past the the dusty shroud at the moment. So we don't know what they are. But they're there. I don't have a ton on this. Kind of partly because there isn't a ton on this. But yeah. So those are weird. Anyone have any of their own theories? So we have a compact object with a bunch of gas and dust around it that is obscuring whatever is inside.
Could it be a cloud that's trying to form a storm, but the tidal forces keep wrecking the deal?
You know, maybe. I'll need to see if there's any papers on that one. Huh. But yeah, I could see a protostar that started forming and then had the less bound gas and dust sort of ripped away from it as it interacted with other things.
Can you go back?
Yeah, this is the hydrodynamical simulation of if it was just gas.
So doesn't that look like something that's had tidal damage?
Yeah.
But that's just simulated.
Yeah, this is simulated.
Okay.
This is what we actually observed.
You need a bigger telescope.
I think EHT would have a hard time following this because, we're eventually going to enter the era of the extremely large telescopes, but I don't have no one I know has time on those.
So we were assuming that you were assuming in 2012 or 2013 that in 2014 it would get eaten. But
Yeah.
then it looks to me like it kind of got bounced off. like it hit something denser than itself. on
Yeah,
that
it
piece of
did.
disk,
Yeah, you
and
can
it
see
comes
a,
out.
yeah, you can see a little, oh, you can see a little bit of a tail coming off of it, so it did get a little tidally disturbed. But it still stayed generally compact.
Right, so there has to be a gravitational force there.
Mhm.
Your two stars with a, dusty, with a dust ball around it, probably is the better candidate at this moment.
Mm-hmm.
Cause it would have to have enough gravity in itself to keep itself together. As
Mm-hmm.
it hit that denser area.
Yeah. But yeah, this if you want to read more, I do have a couple of like nature papers that are like short little things that do actually have a lot more detail about these. But they're more, these are much more the realm of Dr. Anna Kirlo. So yeah, I talked about what I know of these, but yeah. But I do like the but yeah, the leading idea is the binary stars that have collided, I think made a new star, but now have a lot of gas and dust that are left over from that collision. Yeah. Any other comments or questions?
This is Eric. I just want to make sure I'm looking at these pictures correctly, that I'm
Mhm.
interpreting it correctly. The white plus is the Sagittarius A star, correct?
Yeah, I think over here they started to crop it so that you could see if stuff was already on the other side of it. I'm not sure what they were doing there.
Okay, because my question was gonna be on the 2014 one.
Yeah.
What happened to the bright
Yeah.
spot?
So I believe this is as it's starting to go around, it's going fast or something. I'm not sure why it kind of disappears. I know its velocity increased a lot during those few months, but I'm not sure why it sort of appeared to disappear
Okay.
in that image.
All right. Thank you.
Of course. Okay. Shall I move on?
Yeah.
Okay. Okay. So zooming out one more time, we are going back to the nuclear star cluster. So as a reminder, that is about the inner 30 light years-ish of the of sort of diameter around the black hole. This is a 3-color image taken in infrared. It's color coded to blue, green, and red in 3 different wavelengths. It was actually taken with the Wide Field Camera 3 on the Hubble Space Telescope. And this was data that the Galactic Center group obtained, I believe back in 2010, I think. But yeah, this is our own data. Actually, we got time on the Hubble Space Telescope. Before I was even in the picture. Okay. So, to recall, nuclear star clusters are generally low mass older stars and a very dense region of the galaxy. So we do have a couple of formation scenarios for the nuclear star cluster. The reason why we definitely want to figure this out in our own galaxy is because this can inform us on the formation of nuclear star clusters in other galaxies. Since our galaxy is the only one in which we can individually distinguish the stars in the nuclear star cluster of a galaxy. So the first one is in situ formation, which means that the stars formed at or near their current locations. From this formation scenario, since the galaxy has gone through several cycles of star formation, we would expect these stars to be several billion years old, but not as old as the galaxy, and be generally metal rich. So this would put us more toward 5 billion years rather than like 12. The other idea is that we may have had globular clusters infall into the giant gravitational well at the center of the galaxy. So in this scenario, we would have globular clusters in the halo that would be attracted to the gravitational well, and would fall in. Since globular clusters are very are about the age of our galaxy and were not formed when the galaxy had undergone several iterations of star formation, then we would expect these stars to be near the age of our galaxy, as well as being very metal poor. And when I say metal poor, metal rich, I mean all elements aside from hydrogen and helium. So these are the two scenarios that we're working with. Now, the project that actually motivated me to do this talk in the first place was someone in my lab group, Zhuo Chen. Sorry, I should say Dr. Zhuo Chen, because she just defended her thesis. She did her work on deriving the star formation history of the nuclear star cluster. So the idea for this is that you take the current observations that you have, and then you fit statistical models to those observations to find the model that best fits. And parameters that I essentially let loose to find the best solution include ages, metallicities, how many bursts of star formation happened, and using those different ages and the different formation scenarios, then you can construct the star formation history of the thing you're looking at. And this is possible with a lot of fancy modeling software that Dr. Matthew Hosek, who is one of my mentors, had written, and I will not bore you with the details. But it is a statistical thing, and so the two things that are important here is it's a statistical thing, and the results can generally be trusted. Okay, so with the model, since we're fitting the model to the observations, what data are you using? Because your model is only as good as the data you're putting into it. So we have two data sets. One of them is in blue, the field of view is in blue. Both is from the Gemini telescope on Mauna Kea. And it has hundreds of thousands of stars in it. However, all of the stars in it are seeing limited, meaning we don't have, it's like what everyone sees with a regular telescope. It is not AO corrected or anything fancy like that. In red, we have a few littler fields taken using the very large telescope, VLT, that are AO corrected. So this means that they do have their positions and any spectroscopy corrected for any atmospheric turbulence. The Gemini data set, the data we don't have spectroscopy for, meaning we don't have metallicities. However, for the AO data set, that does mean that we do have spectroscopy. And we do have metallicities that we can input into the model. So this is a different view of the same data set. So along the y-axis here is the sort of number of stars per square arc second on the sky. For the seeing limited data set, it's much smaller. And then for the AO set, even though it's sort of radial coverage out from the black hole is smaller, it does have a higher number of stars, which is more like 1 star per square arc second on the sky. And we can also, additionally over here are the number of stars that we can see with good accuracy at each magnitude. So the shaded region are stars that you would take from the data set to do your science. The non-shaded regions, these are stars that, due to the conditions of the observations at that magnitude and higher, they're too dim to really get good readings on. So in the AO data set, we can end up using dimmer stars because the data is still good enough. But on the seeing limited data set, even though we have like 100 times more stars, they have to be brighter. This becomes important. Well, this became important when Zhua Chen was fitting the models, because she found that the ability to get a good fit with the models was much better when she primarily used the AO data set instead of the seeing limited data set. Because the AO data set had more constraining power, then she was able to fit a model that actually hit all the data points. So this is just a plot of the de-reddened magnitude of stars versus their temperatures. So all of the X's are observed stars in the AO data set, and the colored regions are what the model predicts where stars should be. And the more yellow it is, the higher probability there should be stars there. So the AO data set had better constraining power. Additionally, the thing that she did in her project that was unique to a lot of other models was that she had metallicity data. A lot of other projects just fixed the stars to solar metallicity, which isn't how a lot of stars in the galactic center are. The galactic center actually has a very wide range of metallicities, from very metal poor to very metal rich. Tendency is very metal rich. And the model, when metallicity is free and you use the AO data set, you fit the observations a lot better than you do if you fix it and if you use the seeing data set. So you can see here that the model, when you fix it to solar, leaves a lot of stars unpredicted. So the findings in her report were very important for determining how the metallicity of stars affects our projections of the ages of populations, and what data sets should be used for these kind of studies. So the findings of the work in the end, the best fit model was a 2-burst star formation history. The first burst of star formation would have been most of the stars, about 90% of them. And they were very metal rich. And they would have been about 5 billion years old. So they would have formed about 5 billion years ago. Because of the lower number of stars in the AO data set, we do have a pretty high margin of error, as you can see. However, she found that if you fix the metallicity to solar, then systematically this number goes up by 3 billion years. So if you fix the metallicity to something that's solar, which is more metal poor than what is actually observed, then you get predictions that the nuclear star cluster is older than it probably is. Additionally, the second burst, which has an unconstrained age, is metal poor. So overall, the idea that this data suggests is that most stars formed in situ. However, there are a population of older metal poor stars that likely came from an infalling globular cluster. So the nuclear star cluster probably wasn't just one, probably wasn't just one or the other. It was a mix of both, even though it was probably predominantly in situ formation. But the model suggests that we probably did need a globular cluster to explain older but metal poor stars. Those are the mysteries that we. So these are I guess the summary of the mysteries I've gone over tonight. Paradox of youth. We don't know what G objects are and how the nuclear star cluster formed. Though, in my opinion, the nuclear star cluster formation scenario is the one that we've made the most progress on. But ta-da!
Okay.
Very good.
Thank you.
Great.
All right, let's open the floor for questions. Anybody? Step forward. Okay, so we don't know what the G objects are, but they are higher density areas, correct?
Yes, they are.
So it's
They
kind of a gas dust cloud.
Yes, there is some compact mass at the center of them that holds on to this dusty shroud that allows them to orbit like a star but look like a gas cloud.
Well, protostar.
Yeah, or
Trying to form in this sea of crashing gravitational waves.
maybe, or two stars that collided, and this is the car wreck, so to speak,
Yeah,
left over.
Uh,
yeah. And actually, how much difference is there between those two objects? Minor
Considering
difference,
that
really.
I mean, considering that two colliding stars would be forming a brand new star, that now has its own age and everything, both would be making a new star.
Right.
One would probably be making a higher mass star, and that would live shorter. But yeah, so either one would be star formation of a kind.
So the new radio telescope that they're building in Nevada, you see information on that one?
What's it called?
It was in the Giant Telescope last month, I think, and it's supposed to be like several thousand small radio telescopes all linked together via supercomputers.
Okay.
And I think they're it's several kilometers by several kilometers across, like 16 kilometers by.
Yeah, I hadn't heard of that, but if its size is larger than ALMA or the VLA,
Yeah.
then it would definitely it would allow us to cover a larger baseline and give us more detail on the sky.
That would give you better resolution, wouldn't it?
Mhm.
Almost,
And that's what you need.
almost over. It's almost done.
Yeah, so if we can get better resolution in that area, radio objects would be better resolved. However, that doesn't help us with most stars in the area because most stars are not O and B type stars typically aren't visible in radio.
Right.
It's only things like masers, which are old stars that are spewing out at a, like very particular wavelengths due to something in their atmosphere that they look bright in radio. But I suppose you would be able to get better precision on Sagittarius A star.
Well, what about the G objects? Shouldn't those be
The
giving?
The G objects are faint and infrared, but as far as I know, they don't emit in radio.
Okay, so they're not cold enough for radio.
No.
Okay.
Yeah. As far as
Okay.
I know, no.
Okay.
That they're pretty enshrouded in any other gas and dust in the area, so they're usually pretty hard to pick out too. That dusty shroud kind of makes them hard to track, actually. It's honestly almost like a stealth device.
Right. Well, I was just thinking that maybe the dust and so forth, that's what radio is really good for,
Mm,
is that stuff, but if it's too hot.
yeah.
Then the wavelength.
I'd have to look that up. I don't actually I'm pretty sure that we haven't seen them in radio.
Okay.
Yeah. Sorry, I don't know. It's probably written down somewhere in my notes. But
Anyway,
sorry.
anyone else?
They're Borg cubes.
Borg cubes. Oh dear. Anybody else got questions?
I know I kind of answered some during the talk.
Yep, you did. All right.
Well, I have one. Do you have any idea what the G stands for?
Ghost.
Ghost?
What does it stand
Yes.
for?
Yes, or a ghost.
What does it stand for? I was just reading that paper earlier, so give me 1 second. Yes, stars. So called.
The objects. Ghost that we didn't talk about. The computer program. Probably something dirty. Now I'm gonna get it.
I've got nothing.
Actually,
They're just called the so-called G objects.
Actually, I got one other thing that, there might be some people in the room or out there in Zoom land, that don't know what the metallicity means.
Sorry. Metallicity refers to essentially the percentage of the star that is not hydrogen or helium.
Right.
So
Silicon and so forth.
yeah, so anything heavier than 2 protons and 2 neutrons is called a metal.
In astronomy.
Yeah.
In astronomy. Yeah. I mean, Joseph cringes whenever I make the back of the envelope calculation and substitute pi as 1. So
Difficult to hear.
Kirk is having it.
Let's go.
hello?
We're still here. We can still hear you. It was just the screen went to something else.
I don't think she can hear us.
No, I can hear you, but
You're back.
the image is frozen of Doug's face tilting to the side.
God, no. That's horrible. Now you'll have nightmares.
No, not really.
What happened is our camera disconnected. 1 second.
Okay. Since we're just answering questions now, I'm going to stop the share though. Is that okay?
Yeah.
Okay.
Well, we can still see you moving. It's just the camera here. is stuck.
Oh, oh,
There we go.
hey, now I see Eric.
Oh my gosh.
It's better than looking at Doug. So,
Uh,
if we have nothing else, we can move on to announcements and so forth.
Okay.
So all of you out there in Zoom land, if you'd hang on with me for a minute.
Good job, Rebecca.
Yeah.
thank you so much. I hope
Yeah.
y'all had a good time.
We did. It was wonderful seeing you again. And we hope you keep in touch and let us know how things are going.
Totally.
Yeah,
I love you all.
and we love you as well. We miss having you in person. Could use you this weekend, or no, the September 23rd for Astronomy in the Park. We have a bunch of Girl Scouts coming, so you'd be a great we would show you off as our trophy, see what girls can do. All right, let's start with that. So September 23rd is the next Astronomy in the Park.
Actually, let me put it back up.
And I was informed a couple of days ago that there will be several troops of Girl Scouts there. That means we need telescopes. We need more than just Eric and Bill out there. Where is Bill tonight anyway? Everybody talked bad about Bill. He's not here.
lose. Oh, I don't.
So we need as many telescopes as we possibly can out there because we're gonna have a whole bunch of Girl Scouts out there. Of course, it also means that we might get cookies too. It happened the last time. So they're gonna be working on their merit badge. And so they're gonna be needing to look through our scopes and so forth. And they'll have, I'm assuming, lots and lots of questions. Talking about volunteers, we do have a volunteer problem. When I first started with this group in 2004, we'd have 8-10 telescopes out at every at Delta at the park. And we started doing that, 8, 10, 12 telescopes showing up. The numbers have been dwindling really badly. We really need more people to show up with their telescopes, or our public outreach stuff is going to be in trouble. I can't necessarily tell people teachers anymore, yes, we will be there. I'm now answering that question with, let me see if I can get volunteers. So talk to the other members that aren't here or aren't in Zoom land. If they've got a telescope, we need them to, I send out the requests via email, but most of the time all I'm hearing is crickets. So like I said, we need to know if we have more volunteers, and if not, basically I'm gonna like I said, just tell teachers, I don't know if we're doing public star parties or not. That's where we're at with that. I do need another scope or two out at Discovery Academy on the 21st. We usually have 4, we can make do with 3. I assume Bill will be there. I will be there. I'm gonna check with Frank. I was hoping that Frank and Darlene would be here tonight. Let's see. The other question I had out there is, so October 14th, we have a annular eclipse, or we'll have a partial eclipse here. What are we doing? Are we gonna get together? Is anyone gonna be in town? It's on a Saturday morning. We're going to Winnemucca, okay? So I need to know. What's that?
I'm paying up there myself.
Okay, so I need to know if anyone's gonna be in town. Do we have so basically all the hydrogen alphas are gonna be gone? Okay.
Correct.
All right. So basically, you're gonna be in town and you want to be available, I'm gonna ask, I've asked Annie, with the Office of Education here, if they were thinking about doing anything. And then on the next subject is, Yatsik, well, what is his last name? The astronomy professor for, Delta is asking us if we are gonna be able to, have volunteers for his students. And that is basically the Friday before astronomy in the park, first quarter moon. I need to get back to him and let him know if we have volunteers or not. And so I need to know from you, that are listening here, are you available on that Friday night? Are you willing to go to Delta and, set up a telescope, and help the, astronomy students there? Because there are astronomy students at Delta. Delta has telescopes, they bring them out. So we just need a couple of our people there. So when the public comes out there, we have some exposure there, and we can help the Delta students, because the Delta students, well, they don't have the experience that we do. Okay, so they want us out there to help them, show them how to use the telescopes and what to look for. And then in some ways, explain to them what they're looking at. But it comes down to, you know, you out there in Zoom land and here in the room, do we have volunteers to do this? So all of you have my email address. You have my phone numbers. Call me, let me know. I need to know what to tell Yatsik from Delta. I gotta get back to him pretty soon, so if you guys can.
What's the date?
It'll be September 22nd. It'll be October 20th and so forth. Yeah, like I said, for Delta, it'll be the Friday before, because the astronomy in the park is first quarter moon. So what we always try to do is something close to the first quarter moon, so we have the moon to look at minimum. So, like I said, I need to know who's available on the Saturdays, who's available on the Fridays, and if you can do both, that would be fantastic. If not, I mean, I understand, but we need to know.
Can I mention something about the September 16th event?
Absolutely.
September 16th is the high altitude star party at Pedley Hill. But at noon that day, from Pedley Hill, I know it's only like 19 degrees from the sun, but the moon will partially occult Mars. Possibly totally occult it, possibly partially occult it. It will not in Stockton. So there's a line of it happening and it not happening between here and Pedley Hill. So if you want to see it, you can go to Pedley Hill, and it's a few minutes before noon. Daytime occultations. Actually, if we can see it, it'd be kind of cool.
Yeah. You're gonna video it?
I'm not gonna make that one.
You're not gonna make it?
Pedley Hill, but I'm not gonna make it by noon.
Do you know what time?
About 5 minutes before noon.
I mean,
Give or take an hour. Sorry for my inaccuracy,
Oh.
but give or take an hour. And again, forgive my inaccuracy, but I believe it will happen there and will not happen here. It'll be a near miss here. And the moon will be a very thin crescent, like I said, only 19 degrees from the sun. This will be on the dark side. So you'll see the crescent and you'll see Mars. Then from Pedler Hill, Mars will get eaten by the dark side of the moon and then come back. But from Stockton, it'll just go by and you'll never know anything was happening. You can't see the dark side of the moon. Very interesting event nonetheless.
All right. All right. Our next speaker will be Jeff. On October 14th. So make sure we get a whole bunch of people in here, bring your rotten fruit and vegetables and so forth.
And I'm bringing cookies at night too.
Woo, cool.
And it's possible that we let you-
You get fruit, we get cookies.
Well, Glenda may actually make some. So,
Ooh.
I don't know, I'm just volunteering her without her.
Yeah, that's the good.
So, All right. If that's it, anyone have anything else?
I don't think
So next month, Tim will be back with us. Hopefully he's having a wonderful day hiking in the
Mike already saw something really cool, but not cool. I'm gonna let Mike. Man, Starlinks. They're horrible, but they're awesome. Starlinks.
yeah,
There's a railroad street of dots.
Yeah.
Really cool at the same time.
Boo, Starlink.
Yeah, well, they're shortly after lunch. It's like one of these airplanes. Flying behind, except they were a little startling.
so Rebecca,
We actually saw two chains.
Rebecca, I'm thinking the people using CAC should warn Elon Musk that if he doesn't knock it off, he will start shooting him down with that sodium vapor laser.
You know, Musk has actually made a comment to Space Force saying it doesn't matter if you shoot at them, they won't get disturbed by the laser. And Space Force is like, well, we have a protocol that we can't point the AO laser within a certain range of any satellite. You know what Europe does? You know what Europe does? They just shoot the laser. They don't turn it off.
Then we should do it too.
U.S. Space Force. Eh. I have opinions. I grew up and I have opinions now.
Go get him.
Cranial pressure.
That's right. Take care.
In the laser acronym, you can, instead of amplified, you can call it oscillated, and then it's a loser. And then and then there's no protocol about shining a loser at the satellite.
There you go.
You know, the laser hits a satellite and it destroys a satellite. You're no longer shining a laser at a satellite.
All it would do is make you go blind for a second anyway.
Wait, it's a sodium laser, right? What's it gonna do to a satellite?
No, I don't know.
Nothing.
Disrupt the communication?
It could for a moment. But.
What?
you know, I said it could for a moment. Obviously, if Europe is doing it, then there's no problem.
They really.
Yeah, I mean, I understand for shutting it down for airplanes,
Yeah,
but none of the satellites, none of the modern ones at the very least are even moderately affected by them.
right.
Meanwhile, I'm sitting over there in the observing room being like, we have to shut the telescope down for 3 minutes while we were trying to take a 15-minute exposure.
Right, exactly. Right.
Ah,
You have reason to be upset with it.
To possums and feral cats, I was like.
Yeah, Elon Musk is starting to irritate me.
oh, he has irritated me for a while. I'm in LA. The tunnel project?
Oh, yeah.
All the Teslas?
That's expensive. That's our business.
Should I stop recording?
Yeah, we should probably stop recording.
It's on